All right. Hello, everyone. How's it going? How is everyone feeling today? Is everyone feeling relaxed? Did everyone have a wonderful sleep after finishing their assignment? Well done on finishing assignment 1. You've got 2 whole days of freedom, but also 3 full nights of sleep. I mean, that's pretty incredible. The next one will probably be released on Thursday this week. And the reason for that is because we want to give you the maximum time to find it. And it will be due at the end of week 10 to give you the maximum possible time to complete it and to get through it all. And as bonus, it's like quite good way to study for the exams as well, because the exams are all about linked lists, and so is the assignment. So it's going to be super fun. Anyway, I hope everyone is ready to do more linked lists today. And nothing is glued down, so we're not even held back. Don't be scared for assignment 2. I reckon assignment 2, the first stages are easier than assignment 1. All right. Okay, so let's start. Whew. Okay, let's do it. Let's go. What am I doing? Why isn't... Here we go. Here we go. Okay, so what did we do yesterday? We watched a keyboard being unglued from the desk, which was actually the height of my excitement. I could hear it breaking as someone was trying to pull it off. We looked at multi-file projects. We did malloc and free, kind of. We kind of just touched on it, but we will do more of it, don't worry. And then we did a little linked list action. So we did creating a list, kind of inserting a node at the head of the list and traversing the list when we were printing it. So we did a few things. All of those things were done in haste. So we will be going over more things today. We will be drawing more things today, and we will be slowing down the pace a little bit. Also, in very good news, I can tell you that linked lists is the last new thing that we will really learn in this course, but we're just going to be doing different things with linked lists for the next few weeks, and then we're going to revise for the exam. So things are looking up finally after yesterday when we covered about 7 new things, which was probably not that fun, maybe a little bit fun. I mean, a few of you fell asleep, so it couldn't have been that fun. Okay, so today I am hoping to do linked lists, inserting anywhere in a linked list. So you're not always going to insert at the head or the tail. You're going to need to just insert into a linked list wherever. Maybe, depending how we're going, we will do deleting nodes, okay, also from a linked list. But let's just see how we go. Otherwise, we will do them on Tuesday next week, and that's not a problem either for us. So please don't stress, and keep letting me know in the chat if I should slow down or speed up as well. And I can go over anything as well that you need to go over as well today. Okay, fantastic. There is also appears to be a huge delay between me speaking and the stream going through. So excuse me if there's then a silence whilst I wait for your question. Questions. Okay, live code, and we're going to be doing some magical linked lists, so that's amazing. Okay, so let's revise. Who remembers what a linked list is? Who's here for the party of the linked list party? And this is when I wait and wait and wait. Yeah, it's linked list is made of multiple nodes, and each node has, so it's not made up of pointers, but the pointer holds the address of each node so that we know where that node is, because they are anywhere in the memory. Okay, so basically, if you have an array, okay, we know that an array is a contiguous piece of memory. So with an array, if we say, okay, I want an array of 100 elements, That means at compile time, the compiler is going to allocate, and it's an array of ints. So it's going to allocate, and each int is 4 bytes. It's going to allocate 400 bytes to this array somewhere in memory, but that chunk of memory has to be contiguous, which means that each 4 bytes have to be one after another. So they're not kind of separated. They're not all over the shop. So let's say I've got this array. It's got 100 things, and I fill up those 100 things, and I need to have 101 things, actually. So what happens to that extra thing that I now need to have in the array that I cannot have in the array because my array has now run out of space? What do you reckon happens to that? What do we reckon happens? So I've got this array. How can an array run out of space? Because I've reserved 100. I've reserved enough memory for 100 ints, right? So if I need an extra int, that memory is done at compile time. So once the program is running, that memory is set in stone. Yeah, so I could do some magic, and I could do allocation of another bit of memory of exactly the same size, but it's very difficult to do, right? It's not an easy thing to do. Because an array is contiguous, I want that memory to be contiguous, so it all becomes not that pleasant, really. So basically, we have then linked list as another data structure available to us, because a linked list, I can request nodes as I need them, right? So I'm not going to run out of nodes because I can just take an extra one whenever I need it, because I'm mallocing the space for them on the heap, right? So and that piece of memory for each node, it's not contiguous, right? So my linked list, even though we're drawing it sort of like in a line, that's really not the right visual, right? Because the nodes can be anywhere, all over the shop. But we draw it like this just because it's easier for our brains to process. But that's not how it is located in memory. That piece of memory can be anywhere. And that's why each node, we have a pointer storing the address of each node so that we know how to get to each node. And, by the same token, if I request this array of 100 elements and then I only use one index of that array, I've now wasted a whole bunch of memory as well, right? And there's nothing I can do about that. That's just what it is. So obviously with 100 ints, it's not going to make a big difference to your efficiency. But, think of much bigger arrays that will take up more memory, and then, you don't use them. So it all kind of adds up in more complex situations. So that's where the linked list comes in, because I request nodes and I take nodes as I need them whilst the program is running, which means that I have, I take a piece of memory, I malloc a piece of memory. So I allocate a chunk of memory, and that malloc function will return to me the address of that memory. And the way I connect up these series of nodes of a linked list is that each node has the address of the next node that will follow it. And that's all it has, right? So I cannot just say, okay, I want to see what's in the fourth node of a linked list. I will have to go through the first, start at the head. So I start at the very top node, go to the second, go to the third, to be able to see what is stored in the fourth node. So unlike in an array where I can just do random indexing and I can say, okay, I want to know what's in the fourth index, and I can just go to it because the memory is contiguous. So if I know where an array starts, I will know where the fourth item of that array is as well. But in a linked list, because the memory is spread out everywhere, only the node knows the one that's coming after it, and then that one knows the one that comes after it, and so on and so forth. So you can really, you just kind of follow a little scavenger hunt, but you have to go to one node, then go to the next one, then go to the next one, then go to the next one. Is there a limit to what and how much we can store in one node? Not particularly, but within reason, of course. Depends, on the context. But I can have in a node, I can have an int, and I can have a char, and I can have an array in there. As long as I have the pointer to the next node, That's what kind of builds up the linked list. That's really one of the like kind of key components of having a linked list structure, is that I have that pointer to the next node. So it's really how you defined your structure of a node, and you can have many different things in it. The reason we're just using int data and then struct node next pointer is because it's the easiest way to demonstrate the actual concept of a linked list. I don't need to fill it up with 70 different things for you just to understand the foundation of what it looks like. But later on we can, try different things. So in this course, right, we're only learning a linked list that goes one way, right? That's not to say that you don't have different types of linked lists, okay? But we're not touching them in this course. We're only going to go in single direction going forward, and that's it, which means that you only have one pointer in the struct node, and that pointer is pointing to the next node after it. So that's what we're doing here. Okay, so the very beginning of the list, because if I want to be able to, actually even access the linked list, I need to know where to start. So the address of the very first node is stored in a pointer, in a variable, and usually we call that variable the head of the list, okay? So the head has it's not a node itself, but it has the address of the first node. And then the last node will point to null, right? Because there's no there's no node coming after it, and we denote that with a null pointer, which means that there is no memory, there's nothing after it, it's a null. And that allows us to be able to traverse our list, because we don't want to access null memory. That is quite an issue, and it will cause everything to go crash and stuff. And also a bit of a problem, okay? So and you'll run into that a lot, okay? Where you will by accident access null memory, and so you'll see this error a lot as you start working on your assignment, and also just as you start working with linked lists. Okay, there's I feel like I've talked a lot. I'll just talk a little bit more. Why not? Okay, so we're going to do inserting today for the next however long. If you're not ready to move to deleting, I will poll that so that we know, and we will do that on Tuesday next week. There is no lecture on Monday, and I will make sure that we cover everything that we need to cover. So you get a bit of a break on Monday, and a chance to work a little bit more on the assignment. Maybe you can get through stage 1. So today we're going to look at inserting kind of into the list, anywhere in the list, but there's always things that you need to consider when you're inserting a node, right? So first of all, what are the steps that we need to insert a node? 1, I need to malloc some memory for that node, because I need to know that where that node is going to be located. Then I need to initialize the node, so I need to add some data to the node. No, we have time for a Kahoot today. Don't worry, there is Kahoot time today. So we're going to malloc some memory for a node. We're going to initialize the node by putting some data into it and putting into both the data and the next pointer to it. And then depending what, we're going to see what else we need to do. So usually with linked lists, the problems are the same way as when we talked about arrays. You always think about what happens if the list is empty and I have done the first thing, inserted the first node. So you have to make sure that the head is there and that you know where to start the linked list. So if you're inserting at the head of the linked list, you need to consider that. And then you're inserting at the end of the linked list, you need to consider that. So again, those edge cases where you insert at the start, you insert at the end, you need to consider those every time you kind of deal with linked lists. And we will talk more about what the edge cases are as well for deleting. Now with linked lists, you really just need to draw a diagram each time, because then you can really so easily see what the pitfall is or what the edge case is. It's so much harder to do it without a diagram. So I will be drawing a lot, and hopefully that will be just so amazing. You'll have the best time watching me draw my terrible rectangles. Okay, let's have a look at some linked lists. So what I am thinking, and let's maybe do a poll, Sophie or Bella, can I get you to do a poll? Do we want right now to separate this linked list file into a multi-file system? and then work like that? Or do we want to still stay in the main for a little bit longer and stay in one file for a little bit longer? How do we feel? Let's get a poll going. You're going to have multi-files for assignment 2. Okay. Okay, let's separate into a multi-file system, and then we can, we can see where that takes us. It's going to look a lot neater. Okay, let's do that. Okay. I've forgotten. Here we go, and it's week 7. And what I'm going to do is I'm going to make a directory, and then I'm going to okay. I'll keep the one linked list here, and then what I will do is I'm just going to create all of them from scratch and just copy the code over so that you still have the one file, so that you can have a look, if you wanted to see how we built the multi-file as well. Okay, so I'm going to go into my directory. I'm in the directory, and I'm going to make 3 files. I'm going to have a main.c, I'm going to have a linked list.c, and I'm going to have a linked list. You know what? I'm so sorry. I cannot I'm just going to call them that, okay? Because that means that I have less typing to do when I compile. Okay, I'm nothing if not lazy. Okay, great. Let's do it. Let's check, and let me give you access to the files. Okay, fantastic. So what I'm going to do now is I'm going to open those files, and then we're going to do some copying into them. Okay, great. Okay, so the first file we're going to do, I'm going to look at my linked list, okay, and I'm going to do a few things. So the first thing I'm going to do is I'm going to move some things out. Okay, I've got a function definition. Okay, that function definition definitely goes into my .h, and let's just say this is the header file for our linked list program. The header file will have definitions of things we want implemented, and our hash defines. Yay! Okay, great. Amazing. We have some amazing things going on. Okay, good. Let's keep it going. So now let's do, what's the next thing we can move out? Should we move out these 2 things? Or not? What do we think? Or would you like to start with the main file? Because the main file, I guess, is much easier. I'll just copy the main over. No? Okay, good. Okay, so far I've just got one thing in there. It's the print list function, start with main. So I'm going to take this main and I'm going to move it out, and then we're going to see what can be removed from this main. Okay, so the main has gone in here. Now inside the main, this is the main file for our linked list program. We should be making calls out to our functions from here. Okay, good. So, good stuff. So, what does that mean include in the main? Okay, so we're going to include our standard libraries. And now I also need to have access to what of these prototypes I'm going to need, right? Because so when it compiles, it'll take these prototypes and it'll place them at the top of this file. So what are we going to do to also give it access to have my own header file? Yep, so we want to include our header file. So we're going to include, and then because it's our own file, we're going to put it in double quotation marks, and we're going to include the files that we actually want to see, which is ll.h. Okay, so this inclusion here, this include gives us access to the prototypes and all the defines in the header files. Okay, fantastic. Okay, so I've got those. So now what I want to be doing is I want to actually be making some magic here. So right now I've got a lot going on, and we said, okay, I think we really need to, we will need to define the struct node, and we will talk about where we're going to do it in a second. Okay, because from here right now, I'm actually doing a lot of things that I could be doing in a function. Okay, so this bit here, this should really be a function because it always follows the same procedure, right? So to create a function, to create a node, all I'm doing is I'm mallocing some memory and then I'm adding some data to that node. Okay, so always the same three things. I could do it multiple times, and here I have done it multiple times, but it's really just one function, and that function is to create a node. So I think what we will do to start with is we will do a create node function. How does that sound? I'll stay in the main for a second, then I'll copy it into a linked list. So this is what we're trying to achieve. Okay, so we're trying to achieve two things. So to create a new node, we really need to do three things. Those three things are malloc some memory for the node. Then we want to initialize the node with some data. And then we want to, because our node by definition has two things in it, it has the pointer to the next node and it also has the data. We want to initialize the node with our next pointer. Okay, so in that case, if we were creating a function to do this, okay, then what does that mean? We want the input to this kind of function to be. And what do we want the output to this kind of function to be? Yeah, so in the input, you want the data that's going to go into the node. So you want the data, you want the pointer next, potentially. Yeah, that sounds good. And then what will be the output of this node? What will be the output of this function you have just created, okay? So the reason it's not the head of the list is because you're just creating one single node. So you want to then return, the pointer to that node, to that piece of memory. So you want to return where that node that you've just created is, okay? Because remember, it's created anywhere. It's not contiguous. It's not like in any particular way. So you just want to return the memory address of where you've created this node. Okay, great. So we're returning a pointer to a node that we've just created, which means that we are returning a struct node pointer, okay? And we're going to call this function create node because creativity is important. And we're giving it two things. We're giving it the data And then we're also giving it the pointer to the next node, right? Because that's how we initialize it. Those are the three things we need. So we've got to malloc some memory, we initialize with some data, and then we initialize the node with our next pointer. Okay, great. So if we were to do those things, we would just literally take, so we would do the first thing, and the first thing would be where we create this node and we give it some, so malloc returns a pointer to that piece of memory. So I've told it where to store that memory, and I'm not going to call it car, I'm just going to call it new node so that it's obvious what it is actually doing. So this struct new node is where the address will be stored of the new node that I'm creating. And I'm allocating some memory using the size of function, and I'm telling it, can you please grab the size of a struct node and then give me that amount of memory that I will need. Okay, so that means we've done step one. We've done mallocing some memory for the node. Now we need to initialize the node with some data. So to go into our node, the address of the node is stored inside new node, okay? So we want to go to the address and we want to enter into the data member of our struct, okay? And then we're going to assign whatever data we've sent it off with to this new node. And similarly, we then want to do the same thing, but we want to do it for our next pointer. And then we will assign it this next over here that we have sent the function call with. Okay? Okay, great. So we've done these things. We've done all this love. We've done the three things. So all that's left now, which means we have done these three things, all that is left now is to return something. So what are we going to be returning from this function? If I can type return as well, which would be really, really nice. What am I returning? What do we think? Yeah, new node. Excellent. Okay, great. All right, now I don't want to have functions in my main.c, right? I just wrote it so that you could see from here to here how it goes. So the implementation of functions is actually inside my linked list.c file. So I'm going to cut this and I'm going to move it into my linked list.c. And this is where we're going to be implementing all the functions that we have defined in here. Now, because we have this function, we need to prototype it. And that prototype is going to go into our .h file, into the header file. So that means we're going to have this function to create a new node. This is the implementation of this function, okay? So .h is where you define what you need, and then .c is where you implement it. Okay, fantastic. So I've got this new node. Things are amazing, okay, things are going well. So I'm going to go to main, and what I'm going to do instead of doing, so let's say instead of doing this here, I can now call my function, okay? So my function is going to, well, I can't really because I'm just going to create the node, but I'm not connecting it to anything yet. So, okay. I feel like, how much can I restructure this code? Okay, let me do the simple thing. I'll take this print list function and I'll move it into my .c file. Okay, let's move this function in here as well. So this is implementation of the print list. So now we've got print list here. Okay, so we've got all our functions, and I'll save them all so that you can see them all and they're updated. Okay. Okay. Are there any questions? Sorry, I keep missing the questions because my screens are different. Put them in the chat if there's any questions. No questions so far. Amazing. Okay, great. So we've now got a way to create a node. Okay. So here we've got a way to create a node. We've got a way to print out a list. Where do you think I should define my struct node? Because nowhere right now have we defined a struct node, right? We've got all this stuff, but it's not going to compile. We don't know what a node looks like right now. No one's defined it for us. There's no structure for it. What do we think? In which file do you think I will put my definition of a struct node? I'll let it go so that a few people can do that. Yeah. Okay, there's a few guesses. Okay, so there's multiple ways you can do this. What fun! Multiple ways we can do this, okay? So we could define it in the header file, but that means that if I have two different people that are implementing these functions, they are kind of stuck in my definition that I've decided is correct for this node, right? So if I implement it inside my linked list.c where I'm actually implementing the functions, if I define my struct node in here, then that means that I'm the one that's implementing it. This is how I define a node. So the code then fits into how I define the node, if that makes sense. Okay, so for now, I'm going to define it in my ll.c, and we can see what happens if we define it in ll.h, but there are potential reasons to not do that, and it, as usual, all depends on context. Okay, I don't need to type it again. What I'm going to do is I'm just going to move that into my ll.c. Okay, now my linked list.c, right now, I'm not including anything. What should I be including in my linked ll.c file? So in my main.c, I've included stdio.h and ll.h. In my ll.h, I haven't included anything. And what do you think I should include in my ll.c? Yep, so we want to include our normal library, standard library, because we're implementing function in here. So we need to have access to the standard library. Do we need to include the ll.h file? I gotcha. You do have to include it, okay? So because this is my header file that might have definitions in it of things that I need for this file, okay? So this is why we include it. So I am going to include the header file because it will contain all the definitions I will need in my implementation file. Okay, great. So now I've included some things. I'm feeling good. I've got a struct node. I've got a create node, and I've got a print list. Okay, I would like to now have a function that will, so we've talked about how we go through, print the list, and that means that we're going through the whole list, okay? So who remembers going through this function and who still understands it and remembers it, or who wants me to draw up this print list again, how we traverse a linked list, because that's going to be important. Maybe should we do that as a, yeah, let's do it again. Good idea. Okay. Should we keep it neat? Do a new one? Why not? Let's live a little. All right. Let's have a look. Okay, I'm going to go through this function over here, this print list function. And let me just get the same, what have I done? Why isn't it showing me my other whiteboard? Microsoft and I not getting along. Here we are. Okay, so this is how it works, okay? So let's say I've got a bunch of I've got a linked list right now, and the linked list looks like this, okay? So I'm not doing anything right now. I'm just going to draw a linked list and pretend like it exists. And I'm going to finish it, so that means that this is going to be null. And over here, I'm going to have some sort of head pointer that's going to be pointing to the head. So I'm going to now pretend that these have memory addresses. Remember that this is completely fake, these memory addresses. I'm literally just making it up just so that we can have ease of seeing. So let's say the linked list looks like this. That means that inside my head pointer, I have the address 0xa, yeah? That also means that inside my 0xa, if I'm pointing to this next one, that means the address here is 0xb. And that means that in my next one, I'm pointing to this one, so the address of this next node is 0xc. And then I finish with a null, okay? So if I were to go through the print list function, okay, basically what's happening here is the first line of code is resetting. It's saying, okay, I want a pointer, and I want that pointer to be called current. And the reason that we do this is that we never ever want to lose the address of the head, okay? So in this case, it might not matter, but you will kind of get to a place where you're doing a lot of manipulation of a linked list. So you may move or change what the head is storing, the address that the head is storing. And this is problematic because if you lose where the head is, then you really lose the whole linked list because you don't know where to start, you don't know where anything is, right? So you will never find that linked list again. That's just a lot of memory that's now gone. So what we're doing is we're just having a pointer where we store the address of the head. So then we're not manipulating anything in the head, but we're rather just using this temporary pointer that we don't care about, and we usually call it current. And that's the pointer that we use to traverse a linked list or do anything basically. So we've got this pointer current, and what we're doing is inside current, we're storing the value of head, which is 0x8, the value over here. Okay, great. So we've got our current, and we start moving through the list on line 31. So we do a while loop here. A while loop is easier for linked lists, or looks neater. I think it looks neater than a for loop, because otherwise you'll have a for loop with all of this. This is the condition. You still can, but it's just a very long line. I think it's a bit neater to do it like this. So the condition is saying, is current equal to null? No, current is not equal to null. Current has a value in it, which means that this while loop is is true, and that means I can enter into the while loop. And the first thing I do is I print out a %d, and I get that from the current. So I go to the address in current. The address in current is 0xa. So that means go to the node. That little arrow means go to the node and go inside the data member. So go into this member and pull out what is stored in it and print it out. So then my printf statement over here is printing out that value, which in this case is going to be 3. Okay, good. So we've got that far. Amazing. So now we move on to the next line, line 33, where we want to, now that we've accessed whatever is happening in the first node, we want to move our node along, because otherwise we're going to just keep accessing the same node. So we access the next node by, on here, seeing what is the next node to it. So the next node, so we access the address at current, so the current is 0xa, so we'll go to 0xa, and then we want to enter into the next member. So that means we're entering into this member and pulling out this address. So now we're holding this address and we assign it to the left side, which is our current pointer. So the current is now going to be 0xb. And then we start the while condition again. So we'll check, is this current equals to null? No, it doesn't. So that means it's true, and we go into the while loop. So now we print out a %d and we go into current data. So we go to the address in current and we dereference it. So it's 0xb, which means I go into this node and I go into the data member of it. So I've got a 5, and then I print it out because I've got the %d over here. And then the next thing I do is I want to move my node along by 1 again. So I will enter into my current again. I'll dereference the pointer at current, which is 0xb, and I'll access the next member of it, which is 0xc. And then I will assign it, whatever that was, which is now 0xc, I'll assign it to the current pointer. So now this is going to be 0xc. Great. Then I'll go back and I'll check my while condition again. So is the current, which is 0xc, equal to null? No, it's not, which means that this is true, and I go into the while loop again. So now I dereference what's sitting inside my current data. So my current dereference is 0xc, and I go into the data member of it. And I print it out. So now I'll print out a 10. And then I'll move to the next line. I'll do the right side first, where I move my node along. So I will dereference 0xc, and I'll go inside the next member of it, which is null. And I will assign it over to the left side. So that means that my current is now equals to null, which means that there is nothing there, right? So null is basically a null, right? 0, nothing, void. There's nothing there. So there's no more memory, which means there's no more nodes to go. So then when I check the while condition now, when I check is current equal to null, yes, it is. It is equal to null, which means this condition is false. And I exit out of the while loop. So I break out over here and I finish this. And so I've got my printed out list and I've traversed the linked list to get through it. Okay, can we do a little poll? How does that feel? Does that make sense? Does that make sense for the theory of how to... And the printing is really, you're printing it out because you want to see something and it's more tangible to understand it. But really it's the traversal that matters. And the traversal, sometimes you will need to stop at a different node, which we will go into. But right now, current not equals to null is the traversal. This over here, when you go current not equals to null, is a traversal that moves you through the whole list. And it goes past the end of the list, right? So the arrow means the same thing. So the arrow is basically dereference current. Okay, so dereference the pointer, which means go to the address stored in the pointer, and also access the member of the struct. So that arrow is doing these few things all together. Okay, so it's dereferencing the pointer, which means go to the address stored in the pointer, and then it's also doing that dot bit, which is go to the data part of that struct. So go into this member of the struct. So instead of doing all of this every time, which could get confusing the way it writes, It basically is doing it all together as a shorthand. You just put the little arrow. Okay, what's the difference between the arrow and current is equal to next? So current current is over here, okay? Current is just a pointer. It's not a node itself, but this bit here, this current, it's a variable that stores the address of a struct node. But it is not a node itself, which means that I don't need to go to any member of that struct, right? So this variable here, this current, it just stores the address. It's not, so that's why here it's just an address in here. And then when I go current to next is dereference that address. So go to that address and then access the next member. I hope that kind of makes sense. Yes, no, maybe, kind of, need more time, doesn't make sense still, and 45% yeppers. But only 55 people have voted. Come on, it's anonymous, take a vote. Let me know how you're feeling. What are the vibes? Just wait for that storm to get even more stormy when we start to insert. I think let's do delete next week. Let's just focus on inserting something because we haven't actually inserted anything yet. Oh. What if you call print list in the function print list, like print list current next? You know what will happen? It will start at that address because print list is expecting just an address. So if you give it current next, it means it will skip one item. So something like this will happen. I'll show you. So we'll do print list head. I'll do a printf here to show you. So we'll do new line. I think it's a great question. And if I do print list, and instead of head, so you've got current next, but I'll do head next. Okay, this is still going to be a mess. Just bear with me. Should we try to compile it just because it's going to be a mess? Oh, you want, okay. I understand what you're asking. Okay. So I understand what you're asking now. You can do recursion, but recursion in foundational computing is an actual nightmare, right? So whilst you're trying to get understanding of what's going on here, to also understand recursion is a nightmare, which is why we don't do recursion here. There's not enough. We used to, but 10 weeks is not enough to also include recursion. So if we have spare time, sometimes I'll do a bit of recursion for funsies. But other than that, we're just going to learn how to do it without recursion. But yes, you can absolutely do it with recursion. And linked lists, they love recursive functions. Why I use malloc and size off? I use malloc to allocate some memory for the struct node. And I use size off to tell me how much memory I actually need. Don't worry about recursion. You don't want that nightmare right now. It's a kind of a fun nightmare, but it's a little bit of a nightmare. So don't worry, we're not gonna, it just means, no, I'm not gonna go there because that's gonna be confusing. Okay, I'm thinking we should make some magic happen now. Well, it's 2:54. It's a rough time to do magic. So what I'm going to do is we're going to take a break. And then when we come back from that break, that's when we will do more magic, and then we will insert into the linked list. Okay, so I'll finish this poll. Thank you very much. I think we need to go over more things, and that's okay. We will keep going over it, okay? And I will keep drawing it up. So let's see if by the end of today we feel better on this poll as well. So let's do 5-minute break. We will come back at 3 o'clock, which is actually 6 minutes, but quick break. what a way to come back. Kahoot now or Kahoot after? What are the vibes now? We're about to fix those mistakes that you're talking about in the chat. Yeah, let's do it. Let's do it after. Let's just keep going whilst we're on a roll, and then we can do a little Kahoot to just like finish off and to get the vibes back that we're feeling, better. So let's just, okay. So the first thing we're going to do, okay. Now, the first thing we're going to do, yeah, okay, I'm gathering my thoughts. Here we go. My thoughts are gathered. Okay, so over here, right, in my main, okay, I've got some serious situation happening where I am actually assigning some data to, accessing a head pointer, then accessing the data component, but there is no definition of a struct, right? So that means my compiler is going to have no idea what I'm going on about here. It's going to think I'm mad, okay? I am including my header file, but there's no definition of a struct here. So it's not really getting any of that. So right now, I can't really do this. What I can do is I can call my create node function to start with. So for a second, if we are to do this, so what I'm doing is I'm just commenting out this piece of code. And what I'm going to do is I'm going to just create one node, okay? So I'm going to call my function, and my function is create node. And I'm going to create node with one, and because remember, create node takes two things. Create node takes some data, and it also takes what's the next thing in it. So I'm just going to send it off with some wonderful things. So I'm going to send it off to create a node with the data 1 and the next pointing to null. Okay. Now, will this work if I just go, okay, create a node for me, you do all the hard work, I'm just here for the fun. Will this work to just say create node and then print it for me, please? Thank you very much. Or what should I be doing? What do you think will be the error here? Not sure what I'm doing here. That's always nice to see. So, okay, it's going to go off to this function. It's going to perform this function, this create node function, and this create node function returns something. This create node function returns the address of the new node. I need that address. Otherwise, I actually have no idea where this node was created or what's going on with this node. So I really want to assign it to something. Let's say I'm going to assign it to head. But right now, I don't actually know what head is. I've got no definition for head. There's no variable to define this, okay? So head is not even defined. So I'm going to say, okay, I'm going to have a pointer that is struct node head, and I'm going to initialize it to null, just for fun, right? So what this means is I'm going to have a variable. The variable is a pointer to a node, and that variable is going to be initialized with absolutely nothing. Okay, I will then create a node and I will assign it to the head. Okay, so what we're going to do is we're going to then print out. Okay, so let's see if this works for us. So I'm going to compile it, and remember to compile, I'll compile all the .c files. Okay, a whole bunch of issues for us to work through, a whole bunch of issues, which is fine. Let's look at the top. So all of these are warnings. And there's a call. Okay, there's an error. Let's fix the error. Okay, call to undeclared library function malloc. So we'll go to ll.c, and what I wanted to point out, we're using this function called malloc, okay, which lives in a different library. So the issue here is, if you read the errors, we just need to include the right library, and the solution is right here. Have you remembered to include the standard library? No, I have not. So I'm going to include the standard library to make sure that this is where malloc lives. Okay, so I want to include this to ensure that you know, I'm able to make sure that I'm able to actually get the situation under control. I don't even know what I'm saying anymore. I really need a glass of water at this point. Whoever was saying first glass of water, that's what I need. Okay, great. So we've solved that error. There's another error here, some conflicting data types, but let's look at the first errors. They're actually warnings, they're not errors. So what have we got here? Declaration of struct node will not be visible outside of this function, print list. Again, incompatible pointer type. Okay, so we've passed it the head. It doesn't like that, great. So we've got a whole bunch of issues, right? So who can help me resolve one of these issues, for example? Why not? Who wants to suggest a fix to one of these issues? So the issue happened here. Remember, the linked list one was working, but then nothing was happening. Put a prototype in ll.h. I've got two prototypes here. There's a print list and there is a create node. And here I've got my create node and print list. So I've got my two and a definition of a node. So what do we think else could it be? Shift print list below struct node. My struct node is here. What else do we reckon we can do? This is fun. Okay, you want to try moving this to the header? We can do that. Let's try that. We can see what happens. Make it available to everything. I'm going to comment it out because I am going to move it back at some stage to show you what happens as well. Okay, I'm going to move it into my header file. Okay, let's see what happens now. Let's see how many problems become resolved. All the problems become resolved. Okay, let's run it now. So I should have one node. If we go to main, I should have one node and that one node should have one. So I should be printing out one. And I do. And then a new line, which is this thing here. Okay, we have only one node, which is a bit problematic. So let's say I want to now build a second node. Okay, so right now what I have is something that looks like this. If we run through the code, this is what's happening now. Let's run through the code first, okay? And then we can go from there. Okay, so I'm gonna erase all of this. Okay, let's run through it now. So the first thing we do, we compile it, then it enters into the main function and it does a few things. So the first thing it does over here on line 30, because everything I've commented out before it, and what it does, okay, I've declared a pointer called head, and that pointer is of type struct node. So what I have is a pointer head, and that pointer is of type struct node, and that pointer has a memory address in it, so I've initialized it to have null in it. Great. Then I go to line 31, okay, and on line 31, I'm going to call the function. Remember, we do the right side first. I'm going to call the function create node, and when I call the function create node, I'm going to give it two things. I'm going to give it a 1 and a null. So I've made a call to this function, which means we will go to our implementation here, and we will go to our create node function, and we will run it now. So this create node function was given this data, so that means that this bit here is the data, and it's also been given this pointer next, okay? So that means that this is the next part of it, Okay, fantastic. So we've got the data and we've got the next. So now we're ready to go into the function. So we go into the function, and the first thing we do is we malloc some memory for it. So on the right side, what I'm going to do is I'm going to call malloc, and I'm going to ask it to give me a node. So to give me enough memory to house a node. So when I call this function over here, which is a standard function, what will happen is that I'm going to get a chunk of memory that is in the shape of a node, and it's going to be created. So nothing is in it, but this node has been created. That's what malloc has given me. And then I'm going to go to assign it to this new thing that I've declared. So I've declared a pointer, and the pointer that I've declared is called new node. And I've asked for this pointer new node to have the address of this new node that I've created, which means that it's going to get the address of this new node that I've created, which is this node here. Now on line 20, what I'm going to do is I'm going to dereference the address in new node and go into the data member of it. So I'll go to the address stored in new node, and I'm going to go into the data, and I'm going to assign it the data that came with it. So this data here is going to be assigned to my node. So it's going to get that data in. Then I will go to line 21. I'll dereference the new node again. So I'll go to this address. So I'll go to this address, and I'll go into the next member of this struct. And now I'm going to assign this next over here. So this next is the same as this next. And I'm going to assign this into my next. So now I have a fully fledged node, and that node in it has 1 and a null. So what I'm going to return is new node, which means that what I'm returning is this address over here. So I'm going to return the new node back to where the call came from. So this create node function, when it's called, the right side is performed first, and this 0xb is the return of it. So then it's assigned to the head. So then my head will now, instead of null, have the address of whatever the function returned, this create node function, which was 0xb. Okay, so that means I've got this in the head. So now I will go to print list, and I will give it the head. So what will happen is I will now call the print list function, and I will give it the address at the head. So I'm giving it this pointer 0xb, basically. So when I go here, I'm going to have this head is actually this address 0xb. So when I move to line 33 to commence my function, I'm going to again make a new pointer, and that pointer is going to be called current, and it's just a pointer, it's not a node. And I'm going to assign that pointer the address inside head, and it's this head over here that was sent. So this is the copy, which means that it gets assigned the address that I called this function with. Then I'm going to go into the while loop, and I'm going to check, is current equal to null? No, it's not. There is a value there, which means this is true, and I go into it. And here I dereference current, so I go into 0xb, so I'll move back to this node, and I'll enter the data part of it, and I'm going to print out whatever it's giving, which is 1 in this case, because there's a 1 stored inside the data. And then I'm going to move my current to current next. So I'll do the right side first. I'll dereference 0xb, which means I'll go back to this node, and I'll go to whatever is stored in the next part of it, and it's null, which means that my current is now going to be assigned the value null. So when I do my next while loop, I'll check if current is not equal to null. Well, it is equal to null, which means I'll finish, and I'll exit out of this function, and I'll return to main, where I was called from. I'll print a new line, which was this new line here, and then that's it, and I'll finish my function. Okay, how does that feel? Does that make sense so far? I don't know what the delay is, but how are we feeling? Okay, no objections. Why was there 2 new lines? It's because, no, there's 1 new line because in print list I have a new line here, and then the other new line is because I wrote a printf new line here. bit lost. Okay. I'll try to do one more thing. We'll insert another node and I'll go through it again. Okay, I'll go through the drawing again. It's not easy, right? But the best thing about it is once it clicks, and it takes longer than one lecture for it to click. What does current next mean exactly? Okay, so when you're doing current next, what you are doing is you are accessing the address inside the next and moving the node along. So you're calling the next current. So you're shifting the node to the next node. So what you're doing here is you dereference current, okay? So once I dereference current, I'll go to this node. That's what it means. Go to the address. And then when I say current arrow next, I'm saying dereference this address and go to the next part of it. So what's stored in the next member. And then assign whatever value is sitting in here into the current pointer. And the current is just a pointer, right? It just has one address in it. So we're trying to move along our list, right? As opposed to standing on one element. Okay. I can see a few people are lost, and don't worry, I'm going to keep drawing and keep going through it. And it's perfectly okay to be lost right now. Okay, just keep trying to understand it. I swear when it clicks, and sometimes it takes 7 explanations for it to click. Okay, and I'll keep trying to explain it each time. Okay, so we've got one node now in our list. So it's a very lonely list because it's only got one thing there. So what I'm going to do is I'm going to insert at the tail. So let's do a function. Let's do a function to insert at the end of the list with an exclamation point because I'm excited, but I know that no one else is. Okay, great. Let's have a look at what this function might look like if we're trying to insert at the end of the list. So I've gone back to ll.c where we implement things. Maybe first I'm going to define it. That's probably a better idea. Okay. So I want a function to insert at the end of a list. What do you think such a function would require from me? And what do you think it would give me back? So if I were inserting into a linked list, what do you think I would want my function to have what do you think the function will need if I need to insert? Yeah, so I'll need the linked list itself. Yeah, I do, because I'm inserting at the end of the list. And the only way I can get to the end of the list is if I go through the whole list. So I'm definitely going to give it the head of the list that I am inserting into. And then I need to give it something else, yeah? Yeah, I'll just traverse the list. And I'm going to give it the value of the node that I want to insert, Because I'm inserting at the end of the list, okay, so it's going to be the last node in the list, my next is going to be null because I know that nothing is going to follow it because I'm inserting at the end of the list, which means that I'm only going to give it the value but not the next, basically. And what do you think will be the output of the list? So you think nothing is going to change. What if the list that I'm giving it has nothing in it? And this is going to be the node that I insert into the list. So it's going to be both the head and the tail of the list, right? So even though I know what the list is, that list had nothing in it, but I still want to insert, and this is the first node that I'm inserting at the end of the list, which is going to be also the head of the list. So what does that mean I would need to return to counter this situation? Oh, you should have access to this code, of course. Can you not see it? Okay, maybe now you should be able to see it. Yeah, okay. So we want to return the pointer to the head of the list, okay? So we want to be able to basically return the head of the list again because that head might change. So go into the directory ll and you should be able to see ll.c, ll.h and main.c. And then this a.out, which I don't, anyway, just that's the executable file. Okay, yeah, you can absolutely join two linked lists together if you connect the tail to the head of the list. And that has been a question in a lab in the past. Yes, you can absolutely merge two lists. Bella or Sophie, can you check if the code is, you can see the code? Is it because I haven't saved it? Let me save it again. Okay, great. So I'm going to output the head. Okay, so if I'm outputting the head, then what I'm outputting from this function is a pointer to a node. Yeah? Is everyone happy with that? Ish? As happy as they could be, I suppose. Is it visible? Yeah, perfect. Okay, great. All right, so I'm going to define it. The output is a pointer to a node, right? So it's a pointer to the head of the list. So that means my output is going to be of type struct node star. And we want to call it append node. Let's call it append node. Okay, or insert at the tail. Okay, and then we've said I'm going to give it two things. I'm going to give it the list, and I'm also going to give it the data that I want to insert. So int data for the data that I want to insert, and then defining it to also give it the head of the list, which means that I give it a struct node head. So this is going to be my definition of this function. So now I will go in here into my ll.c to actually implement the function. Okay, so this function and the comments about this function should be in the .h file. But what I'm going to do, I'm going to actually put them in here as well. But it's just for your readability, not for not because that's the way it should be. Just so that you can see everything together. Okay, so if we want to insert at the tail of the list, what do we want to do? We want to traverse to the end of the list, and then we want to insert node at the end. So let's see what it looks like in a diagram, okay? So let's say, okay, for example, let's do append node, and we're going to send it through with a 6 and the head of the list. Okay, so let's say this is the call that we're making. So that means we want, so first of all, what's the first thing that we want to do? We don't have this node yet, so we want to create this node to start with. Is everyone happy with that? And we have a function to do that. We have a create node function. So the first thing that we want to do before we start appending the node, I'm going to put a step here because I want to create the node that I want to insert. So the first thing I want to do is step 1, create the node. Okay, so the way I'm going to create the node is I'm going to use the function that I've written, create node, and that function wants me to give it some data and also the next pointer. Now, the way I'm creating the node, I'm going to insert it at the end. So what I'm going to do is I'm going to give it some data and I'm going to give it null. So I just want a node with this data over here that I've sent it with. and also I'm going to give it a null because I haven't connected it to anything right now. Okay, the node is just created, but it's not pointing to anything because it's just sitting on its own. I haven't linked it up to anything at all yet. Okay, now remember that this function create node, it returns to me a pointer to that node that I've created. So it returns the address of the new node because otherwise I have no way of knowing where this node was created, and I will not be able to actually insert the node anywhere if I don't know where the node is that I want to insert. So I'm going to have a pointer to keep track of where this node is been created. So after I create the node, the address of where this node was created will be put into my variable new node, so into my pointer variable. Okay, great. Now, let's do it. So, the way we're going to do it is we've just done number 1. That's ticked. So the next thing we want to do is we want to traverse the list to the end of the list. So to traverse the list to the end of the list, I'm going to make a current pointer, and you will become very familiar with that and very methodical. Everywhere you need to traverse a list, you will make a current pointer and you'll point it to head. And then you will have the same structure to traverse. You're going to go current is not equal to null, although this might be different, and we'll talk about that in a second. And to move that pointer along, you will have current next. Okay, so we've got a whole bunch of things happening, okay? Now, do we think that this code will or will not fail? Let's see what this code does if we draw it up. We do need malloc. Yeah, it is. So we do need malloc, and that malloc is being used inside the create node function. So when we have the create node function, it will malloc the node for us, right? Okay, great. Let's see what happens if I were to call this function and try and do something with it. So if I call it, okay, I'm going to call it and I'm going to give it the 6 and head. So the first thing that happens in this function is that that means this data over here is going to be equal to so let me do in purple. So this data over here is going to be equal to 6. So I'm going to have data is going to be 6. And this head over here is going to have, I don't know, we've got one node, right? So right now things are going well. So we've got one node, which means that that's going to be the head of the list. So it's going to get this 0xb. Okay, so I've called this function and I'll go in here and I'll go, okay, struct node, new node, create node. So I'll go to the right side first. I'm going to call the function create node and I'm going to give it this data and null, which means that I'm going to call the function create node and I'm going to give it the data. So this value here is 6, and I'm going to give it a null as the second thing that I give it. If we go up to our create node function over here, this is where the magic happens. So I'm going to get a new node here and it's going to be another pointer, and this new node is going to be assigned whatever's happening here. So we're going to malloc some memory and we're going to malloc the size of a struct node, which means that what I'm going to do is I'm going to basically allocate some memory for an empty no, nothing is assigned next, and data. So I'm going to get enough memory for a struct node. So malloc size of struct node basically creates this node for me, empty and uninitialized. And then I'm going to assign the address that malloc returns, because malloc returns to me an address of this node that it created, or this memory that it allocated where it is. and I'm going to assign it into new node. So I'm going to put in this address into new node. So now I know where this little node is at all times. Okay, then I'm going to initialize it. So right now I have this empty unconnected node, but I want to initialize it with some values. So I've got new node, I'll dereference my new node, and I'm going to enter, which means dereference the new node, which means I will go to the address inside. So the address is 0xc. I will travel to this address, and then I'm going to go into the data portion of the struct, and I'm going to assign it the data that is sitting here. So this data is the same as this one here. So it's this 6 here. That's the one that's going to go into my data. Okay, then I'm going to do the same thing. So I'm going to take whatever is sitting in this next, and what's sitting in this next is this null, and I'm going to assign it to a dereference of new node. So I'll go to new node, I'll dereference it, which means I'll go to this address, and then I want to enter the next member of it. And I'm going to assign it whatever was sitting here, which is null. So this is now going to become null. And then I'm going to return new node. So I'm going to return this address back to where it's been called from. So where this function is, now we're going to have the address 0xc sitting. And that's going to be assigned to our new node. But this new node, just to make it more confusing, is not the same as this new node, right? It's a different new node. So this new node is going to be 0xc. So the output of this function is going to be assigned to this new node. What I'll do then is I'll go to and I'll create a new variable, and this variable is created so that I don't ever lose the head pointer, because if I lose the head pointer, I will never be able to find my list. Okay, I'll never know where to start. I'll never be able to find any nodes. So to keep it safe, what I do is I always traverse a list with a different pointer, and usually it's current, and I just assign it the address that's stored in head. So I'm going to assign it the address in head, which is coming from this over here, and that means head is 0xb. So I've assigned my current the value 0xb. Great. Now I'm going to say, is current equal to null? No, it's not, which means I'll go in here and I'll move my my node up along one. So I'll go on the right side, I'll dereference current, so that means I'm going to go to the address stored inside the current. So I'll go to this address, to this node, and I'll enter into the next thing. So I'll enter my next is null, and I'll assign it to current. So current is now going to be null. I'll check this condition. This condition is no good, so I skip this while loop now, and now I'm going to be ready to insert. Okay, so now if I try to insert anything, remembering that current is sitting at null, what do you think is going to happen? Because I've gone past the last node of the list, and I'm now standing somewhere over here at a null, and I can't assign here to backwards. I can only assign things forwards. So I've gone past the end of the list, and that means I'm no longer really able to insert into the list because I don't know the address of this node here that I should have inserted afterwards. Because what I need to do is I need to have this next link up to this node over here. Okay, so there's two things I can do. I can keep track of the previous node, or I don't have to go till the end of the list. What I can do is I can stop on the last node. Okay, so if you go, this current next is not equal to null, what happens is this stops at the last node, but doesn't go past it. And the reason for that is it's going to keep checking this next thing here. So if the next is equal to null, so current next is equal to null as opposed to the current, it will stop at this node. So when I exit, I'll be ready to insert that node because now I can make this connection. Okay, so now I can say, okay, that means my current next, so that means my current next now has to be equal to, I'm going to assign it the address of this new node here, right? So, which means I will connect them up. So my current next is going to be assigned the address of the new node. And what that will do is it will draw up this connection. So instead of having null here, it will now have the address of this new node that I've created, which means that this is now going to point to this, and then it's going to be pointing to the null. Okay, and then I would return the head of the list. Okay, so sorry. Okay, excellent question. But what if current is null? That is exactly what I was going to talk about next. Excellent question. Chocolates for all. So a bit of a problem if current is null, isn't it? Because as soon as I get over here and I try to dereference a null pointer, I'm going to get into a lot of trouble, okay? You cannot dereference a null pointer. So what that means is I can't go to the address of nothing because there's nothing there, right? So null is nothing there. So if I try to dereference it or go to that address, there's nothing to go to. Okay, so what we need to do, and this is your big thing about linked lists, is always with linked lists, we need to consider those special cases. And that special case is I need to check if the linked list is empty. Okay, and to check if it's empty, all I do is I'm going to use an if statement, and I'm going to see if head is equal to null. And because if you gave me a new linked list, okay, if you gave me an empty linked list, then I can't really do much. All I need to do is just return. What do I need to return, actually, if you gave me an empty linked list? So I've created a node here, and there's nothing in the list. So this is going to be the node that's going to be the head and the tail of the list. So that means if the linked list is empty, then what I need to return is what? What do we reckon? I feel like I'm absolutely cooking you all. Yeah, I'm going to return the address of this new node that I've created. So I'm going to return this new node because this is going to give me the address of this one node that I've just created. Okay, so if the head is null, then I'm going to return a new node. Okay, otherwise, I'm going to do a whole bunch of other stuff, which is this stuff. Have I got enough? Okay. Do I need the else? What a great question. If I had just the if and no else, okay, what will happen is it'll check if head is null, and not in this case because I'm returning, so I'm going to exit out of this function. So you're right, I don't particularly need the else. Okay, should we try it? Well, we've got the function, but we haven't actually called it anyway, have we? So let's append a node now. So, and we're going to see some issues as well. Append node, and I'm going to send it in with a 6, and I'm going to give it the head of the list. Okay, let's give it a whirl, and then you can tell me potentially how I can break it again, because I can break it still. Yay! Okay, excellent. So it's doing it, right? Now, what happens? Actually, can you tell me without me doing anything yet, in what case I might break this? Yeah, It's going to be a lot of linked lists. And pointers. No, it's pointers this week. So what do you think can go wrong here? What if I have this over here? What if I do this and I call this function in here and let's say I give it a 7. I didn't really mean that. I just chose the next number. Anyway, so let's say I've done it this way. What do you think will be the output of this? What do we think will be the output? One and 6. Okay, who else thinks? One and 6 again, even though I'm inserting a 7 here, so it should be 7 hypothetically, 1 and 6. So very good. And the reason it's 1 and 6 is there are no nodes yet. Head is equal to null. So what happened is I've made this node with 7, but I haven't actually assigned it to anything, right? So what that means is I lost this node. I don't know where this node is because I haven't taken the memory address of where it was stored, right? So the way I can fix that is I can say, okay, head is equal to append node 7 head for the first one. And then I can just keep going like that, right? And memory is still allocated, but I just don't know where that piece of memory is. I've lost it. And then I can keep appending. So if I do that and I've stored that first bit, then what happens is I have the whole list. No, I don't. And why don't I have the whole list? Why on this output it's 7, 6? What do we reckon? And then I'll run through the code. I'll draw it out. Yeah. So the reason is because over here I'm sending the append node, but I'm not giving it the head of the list. I'm giving it null. Exactly. So if I give it the head of the list, then it will actually insert it into the list. Okay, let's run it again. So now I've got the whole list, 7, 1, and 6 in the order that I've appended them in. Okay, I'm going to run through the code. Can you please run me a poll to see how everyone is feeling? Because I feel like I've cooked you up. Like I've fried you up. There is no returning linked lists. And I've like really built up linked lists as well. The head needs updating when I add things to the end of the list if I'm adding the very first thing, right? So if it's both the head and the tail. So this is the situation here. This is the situation where I am adding the very first node. And that node is both the head and the tail of the list, right? So then I don't know where it is. I've lost the head of the list. In line 32, what is head equal to? In line, oh, and I've just moved it. It was this line. Okay, so in line 32, this head over here is equal to null. So what I'm sending it to this function is with 7 and null. And whatever returns from this function gets assigned to this head over here. Append node is the function that we just wrote. So let's run through it and let's draw it up. Okay, I'm going to get rid of all of this and I'm going to draw it up from scratch. Okay, let's do it. So let's go, we've compiled, we've gone into our main.void, and the first line of code tells us struct node, so declare a pointer and assign, so the pointer is called head. So I've declared a pointer, that pointer is called head, and I'm going to assign the value null to it. Okay, great. So I've got my first bit. Then I will move down to line 34 and I will go to the right side first. And the right side says to me, I'm going to call the function append node and I'm going to give it 7 and the head of the list. So in this case, what is inside head? It's null, which means that I'm sending it in with 7 and null. So I'm going to go to look at what the function looks like, and the function looks like this. So I've called this function over here. I've given it a 7 and a null. And what that means is that this data over here, because this is the way this data is equal to 7, and this head of the list over here is equal to null. Okay? Great. I will go down to line 53 and I will move to the right side, and it's going to call the function create node. So I'm going to call the function create node now, and that function is going to get the data. So this data here is going to go in here. So 7, and then it's going to get a null. So we're going to move to the function create node. And in this function, I've now got my, on the right side, I'm going to allocate some memory, the size of a node, which means what I'm going to do is I'm going to create this chunk of memory, and this is going to house data and next. So it's going to be in the definition of our struct node, it's going to have data and next in it. So I've gotten that memory, and now I'm going to do is this function malloc is going to return the address of that memory. So what I've done here is I've declared a variable, and that variable is a pointer, and the name of that variable is new node. And whatever this returns, this function here, the address, I'm going to assign it to the new node. So I'm going to assign it the address of 0xa. Great. So now what I'm going to do is I'm going to go here, I'm going to grab the data, so this data over here, I'm going to grab it, which means I'm going to grab this 7, I've taken it with both hands, and I'm going to assign it to the left side. The left side, the arrow is telling me, could you please go to the address stored inside new node and access the data element of it. So I'm going to check what address has the new node. The new node has 0xa. I'm going to go to that address. So I'm going to travel to this address and I'm going to access this data component of it. And I'm going to assign data to it. So I'm going to assign the 7 to this node. I'm then going to do the same over here. I'm going to grab the next component, which is this next over here. So I'm going to grab this with both hands now, and I'm going to travel to the address stored inside the new node and access the next part of it. So again, I'm going to check what address is inside new node at 0xa. I'm going to go into the node here, and what I'm going to do next is I'm going to access the next pointer of it. And I'm going to assign this thing that I grabbed with both hands. So I'm going to access the null into here. So the null is now going to go into here, and now I've got this node. It's not connected to anything. It's just a node with some values in it. But what I do know is I know the address of it, and I'm going to return that address. So I'm going to take this address of this node and I'm going to return it. Where will I return it? I'm going to return it to where I called it from. So that means I'm going to go in here where I've made the node and where I've... So now this is going to be assigned to this new node over here, okay? So this new node is not the same as this new node because we're in a different function now, and it doesn't persist, right? I've got this pointer new node and this new node, which let me do it in a different color so that it's more obvious that it's not the same thing. So let's change colors. So this new node in this function is going to get whatever was returned from this create node function. And that was 0xa was the address that was returned to me. Okay, great. Amazing. We're now going to move here and we're going to check. If the head is equal to null, okay, let's go and check what our head is equal to. The head is equal to null. Yeah? So I'm going to go into this if statement and I'm going to return the new node, which means what I'm returning is I'm going to return the address of the new node back to where it got called from. And it got called from here. So this call that I've made, so this call over here that I've just made, the result of it, which is this 0xa, is now going to be assigned to the head. So my head, instead of null, is now going to be 0xa. Okay, so then I've got my new values and I'm going to go to the next line of code. And the next line of code calls this function again. So it's calling this function again. Let's change colors again so that we can see that it's a different call. Okay, so it's calling the function again, append node, and it's giving it 7, and it's giving it the head of the list, which is right now, no, sorry, I'm over here. And it's giving it the head of the list, which means that the head of the list right now is 0xa. So this is what I'm sending through to this new function now. Okay, great. I'm ready to go. I've called this function append node, so I'm going to move over to here and I'm going to use this function again. The first thing I'm going to do in this function is I'm going to do another function, which is create node. And remember that this data over here, so this part of the call is the data, and this part of the call is the head right now. Okay, so what I'm doing is I'm creating the node with the data. So I'm calling another function, and this time I'm creating the node and I'm creating it with the data. So this data, and I'm creating it with a null because right now all I'm doing is just making a node. Okay, so I'll go up to create node, and in here I'm going to grab some memory and I'm going to build myself up a node. This node is not connected to anything yet, but this node has enough memory to store for me some data and a next pointer. So it's going to be the size that will accommodate our node. And I'm going to take the address of that and I'm going to store it inside the new node pointer that is part of this function. So the address is going to go into 0xb. Then I'm going to take this data, grab it with both hands, so this data here, and I'm going to assign it to the left side. And the left side is saying, could you please dereference this address, which means go to this address and then enter into the data part of this address and assign it that data. So in our case, that data is going to be 1. So I'll assign it in. And the next one is saying, okay, again, take this next that's given to you, so this next here, and assign it over to the new node next. So go to the address stored in new node, which is 0. So go to this node and then go into the next part of it and assign this next that you have been sent to assign. So this null. So this null will go in here. Great. So now I've got a new node. This node is floating in space. I don't have anything on this node. And I'm going to return the new node. I'm going to return this address. So this address here is now going to be returned to where I was called from. And that means it's going to be, no, not there. It's going to be returned over here. So over here on this side, I've got this new address, 0xb, and I'm going to assign it to my other function here. So my other function is new node. And that new node is getting this address, 0xb. Great. I'm going to check if the linked list is empty. So I'm going to check, is head equal to null? No, it's not equal to null. The head has an address in it. So I'm not going to go in here. I'm going to take the other branch. And the other branch is going to give me a new variable. And that variable is going to be a pointer current, which is set to the value of the head, which is 0xa. Great. So I've got that. I've set it to head. So now I'm going to move. So I'm going to check, is current next not equal to null? So dereference whatever is sitting inside address and current. The address and current is 0xa. Dereference, go to that address. So this is my node at this address. So I'm going to go to this address and I'm going to check what is sitting inside the next part of this address. Now I have a null sitting inside here, which means that this condition is true. It's not equal, condition, it's not equal to null. So what happens is I'll exit out of this loop. I'm not going to go into that loop. And I'm going to go to the next thing here, where what I will do is I'll take the new node address. So I'll take this address and I'm going to, again, dereference current. So go to the address that is current and go into the next part of it and assign it this address over here. So instead of null, it's now going to have the address 0xb, which means what I've just done is I've just pointed this node to this node. So now they're connected and they make up part of the list. Okay, how are we feeling? I see people just drifted off to talk about the assignment. Stage 4 is like, you know, it's like diminishing returns, right? So don't worry if you haven't done stage 4. It's not. Do you like my drawings? Are my drawings amazing or are they too messy to understand what's going on? Yeah, look, you've got to draw it, okay? Because otherwise you're not going to stop at one thing, you're not going to stop at the other thing. And there's so many edge cases. Oh, thank you, museum. Displaying, coming to a museum near you, basically. It will get better, I promise. Think about it. You've done like 2 hours of linked lists. That's all. I mean, it's not a big amount of time to understand quite a difficult concept and the code that is associated with it. It's not. So, give yourself a pat on the back. You've sat through this. You listened to all of this, which is incredible. And you've kind of, you've kept it together and it's coming together. Okay. So we have run out of time for Kahoot. I hope that we have a better luck next week, but just let this sit with you. Maybe go and look at the code again, kind of over the next week to just practice what's going on and to maybe just kind of have a little bit of a play around with it and a tinker. Or you can also just leave it and enjoy your Easter long weekend. And then we will come back to it on Tuesday and we will do, some more, like some harder things. And also we'll do like maybe some deleting finally we'll do as well. Because you'll need it for the assignment, how to delete out of a linked list as well. So you will have a lot of linked lists to practice with, so don't worry about it. This week's lab is going to have no linked lists yet because we're always running kind of like a week behind. It's going to have pointers, which will help you with linked lists as well. Okay, so just marinate, cook it up a little bit. You'll do good, I promise. And have like a nice, make sure to sleep a little bit in that small break that you get and in those few days before the next assignment comes out. But yeah, have a lovely week ahead and I look forward to seeing you next week as well. Don't eat too much chocolate or maybe eat a lot of chocolate. Do what you like. You're at uni now, you're an adult. Enjoy. Bye everyone. Oh, actually, no, I want you to give me feedback so that I know how we're going. Because you will tell me the truth when there's nothing involved. There you go. Anonymous truth, please. If you have forgotten, no, if you want to tell me I've gone too fast or you want me to draw something else or something like that. So enjoy your Easter break and feedback, please. Thank you.